Hi, we're Group B, doing data privacy and edge computing, specifically with differential privacy and edge computing. And then we will go over sort of our problem and motivation for our research, and then the objectives we achieved with our research. And then we went through those with our proposed solution that included evaluation for our simulation setup. Then we'll go over our expected versus actual results from our simulation and wrap it up with a conclusion. And then for our problem, I'll pass it on to Group Read.
Thank you, Catherine. So this is our first slide and it introduces the problem we focused on in our research. In edge computing, data is processed in a decentralized way closer to where it's generated. While this improves speed and responsiveness, it also makes the system more vulnerable to spoofing attacks where attackers can fake identities to access or manipulate data. So the traditional privacy techniques like anonymization and masking are no longer enough, especially when attackers use more advanced methods like linkage inference or spoofing attacks. So the differential privacy using lipless or Gaussian noise is a strong privacy approach, but its use in edge environment, especially under real-time spoofing attacks, hasn't been studied enough. So the main challenge is to find the right balance, like how do we protect privacy while keeping the data useful and responsive for real-time system. So for the previous, there is no clear framework for evaluating privacy preserving techniques when spoofing threats are actively happening in edge computing. So that's the gap our research is addressing. Next slide, please. So this is the slide that explains the motivation behind our research and why we chose this topic. Edge computing handles sensitive data close to the source, like on IoT devices or sensors, which makes it more exposed to spoofing attacks at every stage, like from data collection to sharing. So spoofing attacks like ARP, IP spoofing are not only common but also hard to detect unless you have smart monitoring tools in place. Traditional privacy protections are not built to handle these kinds of fast, real-time threats in a distributed environment. So we looked into the differential privacy because it's strong privacy framework, but in practice, many organizations hesitate mainly because they are not sure how much privacy it gives versus how much it affects the usefulness of the data. So that's what motivated us to make on this project. We wanted to simulate the spoofing attacks in edge setting, test how Laplace and Gaussian DP techniques perform, and analyze the trade-offs in terms of privacy leakage, prediction accuracy, and system delay. So our ultimate goal is to design a privacy aware spoofing resistance edge platform that works in real time. Now I'll pass it over to May.
The objective of our Phase 2 report is to explore how effective Laplace and Gaussian DP techniques can protect sensitive data during spoofing attacks. We are focusing on whether these methods can prevent attackers from inferring private information while keeping the data useful for analysis. Next slide, please. We made the following key contributions. First, we conduct a competitive analysis of Laplace and Gaussian DP techniques to evaluate their effectiveness in protecting privacy during spoofing attacks. Second, we use mean absolute error to measure the distortion in query accuracy caused by differential privacy. Third, to assess our impact on privacy, utility, false positives, and the latency, we simulate ARP and IP spoofing scenarios. And then we provide a summary of expected result and actual result of the two DP techniques. And finally, we propose a hybrid framework that combines DP with spoofing detection to enhance privacy and security in edge environments. That's all from me, and I will pass it over to Christina.
Thank you, May. Since now we are very well aware of the problem, and the objective behind our research project, let's now get into the proposed design solution. For our design solution, our proposal is the local model on edge network, and that is done for the implementation of DP techniques. And how is this implemented? This is implemented using a privacy barrier between the data collection zone and the data curation zone, as illustrated on the diagram below. And the way it is being implemented is using the zero trust model, because that helps in making this solution a lot more resilient towards any spoofing or other malicious attacks. The way in which this solution is implemented is using this by applying a noise to the data collection layer, which helps in providing just differentially private answers to the untrusted analyst without compromising data utility. Next slide, please. Now let's look at the different phases on implementing this solution. There are 6 phases involved in it. I'm sorry, 5 phases. One is implementation phase, the log collection, model building, model deployment, and validation. The first part of implementing, we set up a spoofing environment, and it can be done either on an AWS or on a non-AWS environment. There is a victim node as well as another attacker node set on the environment, and all data traffic is being monitored on the environment. The next phase, the traffic and the data transmission that is done on the setup environment is being captured and collected and stored in a data storage layer. Once the data is stored, it is being loaded into a model. The data that is being captured right now in the spoofing environment has activity regarding normal as well as malicious activity. Now in the layer of model building phase, the data is being analyzed and it is being trained such that a ML model like isolation forest can detect anomalies and predict spoofing. The model is trained in a cyclical manner such that it is made a lot more accurate, such that there is like close to 90 to 100% accuracy. Once that model is being evaluated well in its test data, then it is ready for deployment. After the deployment of the model, monitoring alerts are enabled. That helps in identifying any malicious activity or any disruption in the data traffic that is going between the edge layers. Along with that, how do we also analyze and see if there is any compromise on the personal data? And that's where differential privacy comes to play. Differential privacy techniques are also being applied on the personal data, especially on any of the census data which is also being captured during this simulation environment, such as income or any other personal data attributes. So once the technique is being applied, we then move to the next phase of validating if there is any leakage on the data when anomalies are being predicted. And that's where we make a good assessment that neither privacy nor the utility are being compromised during anomaly detection. Let me now pass it on to Catherine to talk a little bit more on how this validation and the model evaluation takes place.
So our evaluation focuses on the Laplace versus Gaussian differential privacy mechanisms, and they're named after their respective distributions. The Laplace sort of pictured below sort of features a sort of double exponential distribution, while the Gaussian is the normal distribution with the traditional bell curve. And for metrics, we're mostly focusing on privacy and the mean absolute error, which is sort of a metric to sort of view the utility of the data with the differential privacy mechanisms. For privacy, we sort of defined it after the goals of differential privacy itself, specifically with the epsilon-defined differential privacy or the generalized epsilon and delta differential privacy. And that is just sort of looking at how much a record can affect the outcome of a function. So if you have two data sets with the difference being a record, an attacker could use the differences to sort of make inference attacks and do a privacy leak. And so differential privacy aims to use either the Laplacian or the Gaussian distributions to add noise to prevent that. And then for another big aspect of our research is to looking at the utility versus privacy trade-off. And so if we're adding a lot of noise to the data, does that affect the accuracy of the function outputs? And so to look at that, we're sort of looking at the differences between the predicted value versus the actual true value and taking the mean of those. And then to further along our research, we want to see how these two metrics are affected during a spoofing attack. And that will be sort of done with our simulation. And then I'll pass it on to the simulation with Ayana.
Thank you, Catherine. In the phase 2 simulation, we have our variables, which is a localhost for the victim, a Kali virtual machine for the attacker, also loaded with an Apache web server, a network that's bridged between the localhost as well as the virtual machine. We have our two data set files, CSV files, which one is given the Gaston method applied, and the other one is giving the Laplace method applied. Our simulation is testing the difference between the DP while performing a man-in-the-middle attack using an ARP spoofing between a network user victim, contacting a web server, which is cloudsend.com, and uploading the data file. The attacker gains access to the same network segment. The first step is to position themselves strategically for traffic interception. This is achieved by sending a false ARP broadcast, also known as ARP spoofing. In this process, the attacker sends forged ARP messages across a local network, associating their MAC address with the IP address of a legitimate device. This poisons the ARP cache table of the target machine, effectively redirecting all the traffic from the web application server to the actual attacker's device. Next slide, please. This capture for the data, we use two different methods. We used one, which is Wireshark, which is a real-time traffic monitoring tool used to network troubleshoot, also view details of transmissions and protocols. And the second one, we use WeGet, which is a command line tool that makes it possible to download files from the internet directly to the actor directory. And we use that on the Kali virtual machine, which is what the attacker is essentially looking at. The next slide, please. From the traffic and data capture with Wireshark, the packet capture reveals critical indicators that show unauthorized interceptions between or manipulations of network traffic. And if you could take a look at frame 19, what you see is a false ARP broadcast. The 192.168.0.204 is actually our victim, and then you see the tell in frame 20, which is telling it, redirecting it actually back to our attacker. So essentially, this is where the manipulation is coming from, where all the traffic will be directed back actually to the attacker instead of the web server. The TCP stream that you see there in Wireshark. TCP stream reveals traffic that is directly between endpoint devices. It allows you to see one true identity. It allows you to see who exactly the traffic belongs to, what type of TCP connection is being used, the sources and destinations, also transmissions for request and response, and any data leakage which may reveal sensitive information, and also plain text. Next slide, please. The summary of a research activities where the differential privacy compared two methods. We compared our data sets of the Gassan-Laplace methods were used in identical structure, but differing how the differential privacy is applied to the actual data set. These data sets were retrieved in a CSV format, both hosted on a Google Drive. Although structurally identical, these files differ in, like I said, the DP technique applied. To download the data sets into the Kali virtual machine, the wget command was used. However, due to the nature of the Google Drive URL, the wget retrieved a bunch of raw content from the file index.html, which is the download page instead of the actual file. And because of this, we were able to retrieve a lot more than versus just a basic web page. It actually renders a lot of raw content code. Next slide, please. So what we're actually seeing here in that wget is the, again, raw HTTP traffic. We're seeing the Google Form CS animation. We're seeing some JavaScript where we'll actually see the DP payload applied, and then we'll see where the DP begins to take place with the data encryption. So if you look on the highlighted line, you'll see before, this is basically all of the Google CSS animation code, which structures the web page for the HTML. And in addition, below that, where you see the program equals data, that is the actual JavaScript payload to begin the execution of the DP encryption. And below that, if you notice, you don't see any commas, you don't see any spaces, you don't see any brackets. That's actually the encryption taking place. Next slide, please. This is where we discovered where the differential privacy actually stops. And this could also be considered data leakage. Through more investigation, we see partially deobfuscated invisible data structure embedded in the Java code or the HTML page. However, in column 13, which displayed from our file, which was the country column, was showing completely in plain text. And that entire block is meant to be consumed by a web app and not encrypted. It is meant to be parsed in browser, and there's no need to obfuscate the basic data like country names. And basically what that is saying is that these names, they are considered non-sensitive, they are considered generic. And because of that, they're actually embedded and hard-coded in the actual HTML language or possibly the JavaScript language. And due to that, it actually omits them from part of the encryption process. This could be considered a flaw. This is enough for an attacker to gain some type of reconnaissance. If they had maybe more type of attacker tools, it could definitely lead to more lateral moves or, more credential sniffing or things like that actually aids them in their attack methods. Now I'm going to hand you over to Arcana for the next slide, please.
Thank you, Anna. Let's walk through our key expectation and compare them to what actually happened during our evaluation. Laplace is like a higher privacy and higher MA. We expect Laplace would provide the stronger privacy, but expected a trade-off with accuracy. MAE. In what in actual, that's exactly what we observed. It had the higher MAE, but did a good job at the masking the sensitive attributes. In Gaussian, it has the better utility in actual moderate privacy, but in actual, it retained the more accuracy. But a small privacy leak was detected in actual. What we expect in the differential privacy, too sensitive information to inference. And in actual, it did reduce the risk, but plain text explore via HTMLs and JavaScript was still possible. So not a complete win. In isolation forest, we detect the spoofing in real time, and we thought it would be the effective for the detecting the real-time spoofing attacks. But in actual, it was, yeah, good accuracy with few false positives. In minimal latency, during the differential privacy with the spoofing, we expect the system to still run smoothly even with the differential privacy and spoofing detection. And in actual, we got the slightly higher, but still good enough for the real-time performance. Overall, we prediction held up quite well. The trade-offs between privacy and accuracy were evident. And while differential privacy helped a lot, there are the still edges cases we need to address, especially with the front-end exposure. Thank you.
In conclusion, the exposure highlights a common oversight in modern web applications, plain text data leakage due to reliance on embedded or obfuscated client-side code, such as HTML or JavaScript. Since the web browser must parse this data for functionality, developers often leave non-sensitive information accessible. However, this opens a door to data inference attacks, especially when combined with other available metadata. In conclusion, while differential privacy is a powerful tool for statistical data protection, it must be integrated into a multi-layer security model. While both methods of DP were applied and examined, they essentially perform the same in terms of data leakage. The DP application should work in tandem with encryption, secure communication protocols, and hardened device configurations. Ignoring the outer layers or assuming DP is a complete solution creates a dangerous blind spot, one easily exploited through common network attacks and web-based data leakage vectors. Thank you. This concludes our presentation.